Good day, everyone. Today, I will give an example, or specifically a set, and then we're going to prove if the given set is a vector space. But first, let's have the definition for vector space first because it is important to understand its concept. Let F be a field and V is a non-empty set from the field. Then V is called vector space over F if the following axioms hold. So, specifically, there are 10 axioms to be satisfied before a certain V or a set is called vector space. Let X, Y, and Z be in V, and 1, C, and D be scalars. Then, these are the axioms. Number 1, X plus Y is in V. Note that this symbol is a vector addition. Vector addition. Number 2, X plus Y is equals Y plus X. As you can observe, it's a commutativity. Commutativity. Number 3, X plus the quantity of Y plus Z is equals to the quantity of X plus Y plus Z. So, again, as you can observe, it's about associativity. Number 4, 0 plus X is equals to X plus 0 is equals to X. Number 5, X plus negative X is equals to 0. Number 6, C times X is in V. Note that this symbol is called scalar multiplication. The C there is one of the scalars. Number 7, C times the quantity of X plus Y is equals to C times X plus C times Y. So, the C had distributed to the X and Y. So, it's about distributivity. Number 8 or 8th axiom. Quantity of C plus D times X. The C and D are scalars. Is equals to C times X plus D times X. The X were distributed to C and D. So, it's about distributivity again. Number 9, C times the quantity of D times X is equals to CD times X. Number 9 is about associative property of multiplication. Number 10, 1 times X is equals to X. It is the identity property of multiplication. So, if these 10 axioms will be satisfied by a certain set, therefore, the given set is a vector space. So, to further understand vector space, let me give you an example. For our example, we have show that the set of R squared is a vector space. First, we must know what is R squared. So, R squared is the set that consists of ordered pairs X and Y such that X and Y are element of real numbers. Let me show you again the definition we had earlier. So, in this example, RF or the field here is the R or the real numbers. RV or the non-empty set is the R squared, which consists ordered pairs in the form of X and Y. So, R squared will be considered as vector space if and only if it will satisfy the 10 axioms. So, let's start to find out if R squared is really a vector space or not. So, let's start with axiom number 1. Let X is equals to the ordered pairs X and 2x, and y is equals to y 2y. So our first axiom is x plus y. So simply, we're going to substitute the value of x and the value of y. So we have x to x plus y to y. And then we're gonna add the first coordinates, the x and the y. So x plus y. And then we're gonna add also the second coordinates of each ordered pairs, 2x plus 2y. So now we have x plus y and 2x plus y, where these ordered pairs are element of r squared or belonging to r squared. By this, we have satisfied the first axiom, which is x plus y is in V. Please remember that r squared is our V. So, number 1 axiom is checked. It is satisfied. Now, let's move on to the second axiom. X plus y is equals to y plus x, or simply the commutativity. So, let's have x plus y. The value of x and y is x and 2x. So, we have the coordinates of x plus 2x, x and 2x rather, plus coordinates x and 2y. So, again, let's add the first coordinates of each ordered pairs. We have x plus y and 2x plus y. Since x plus y and y plus x is the same, we can change their position. So we have now y plus x, and then as well as the second coordinate, we have 2y plus 2x. So again, let's add the first coordinates of so now we have y plus 2y and x plus 2x. As you can observe, y plus 2y is y. So, y. X plus 2x is x. So, simply, this means that y plus x. We can now conclude that commutative property holds for this second axiom. It is also satisfied. Now, let's move on to the third axiom. So, for the third axiom, we have x plus the quantity of x plus z is equals to the quantity of x plus y plus z. For this axiom, we need 3 vectors. So, it's about associativity. So, let x, y, and z. Let x is equals to x to x, y is equals to y to y, and z is equals to z to z. So now we write again the first part of the axiom, x plus the quantity of y plus z. And then we will going to proceed for the substitution for its value. So for x, we have x to x, y, we have y to y, and z, z to z. So, in this, we will going to simplify first the terms inside this bracket. So, again, we're gonna add the first coordinates for each ordered pairs. We have, we still copy the value of x plus y plus z. And then the second coordinate is 2y plus 2z. So, after that, we're going to distribute the first coordinate for the x to the first coordinate here. And then, the second coordinate to the second coordinate as well. And we can get the answer as x plus y plus z and 2x plus 2y plus 2z. So, from this form, we can also write it as like this. Quantity of the coordinates rather of x plus y and 2x plus y plus the quantity or the coordinates of vector z, which is its value is z and 2z. Still there is no changes happen. The value of this is still the same with this one. So from this form, we can also write it in this way. Still, there is no changes happen where we have the ordered pairs x to x plus the ordered pairs y to y plus the ordered pair x to z. Rather, z and 2z. As you can observe, these coordinates is equals to x. So this is x. Y to y coordinates is equals to y. So this is y. And z to z coordinates is equals to z. So this is z. It simply means that the quantity of x plus y plus z. So from this one, as you can see, we have reached the answer, which is simply like this. So at this point, we can now conclude that associative property holds for this given vectors. Third axiom satisfied. So for our fourth axiom, we have 0 plus x equals x plus 0 equals x. So we must know that for all x is equals to 2x, such that 2x are an element of r squared, there exists a 0 vector in the form of course, coordinates 0, 0 that also belongs or an element of r squared. So we write the first part of the axiom, which is 0 plus x. By this, we will going to multiply the value of 0 vector. Of course, we have 0, 0, and the value of our x vector, which is the x to x. So x to x. And then let's proceed by adding the first coordinates of each ordered pairs. We have 0 plus x. 0 plus x is simply x. 0 plus 2x is simply 2x. So x plus 2x coordinates is equals to x, of course. So that's it. And then if x plus 0, we substitute the value of x and 0 again. So we have x 2x plus 0, 0. We are going to add the first coordinates of each ordered pairs. X plus 0 is x. 2x plus 0 is 2x. X and 2x are still equal to x. Therefore, we have satisfied the fourth axiom. 0 plus x, x plus 0 is equals to x. In the fifth axiom, x plus negative x is equals to 0. So, if our vector x is equals to the ordered pairs x times 2x, which belongs in r squared, there also exists a unique element, which is the negative x that also belongs in r squared. Such that if we add the two element or the two vectors, the x and negative x, we get 0. Of course, we know that if we add a number or a variables that, or let's say if we add the original number or the variable and its inverse, then we will have a sum of 0. So the fifth axiom satisfied. For axiom number 6, we have c times x is in v. So let c be a scalar and x is equals to x to x. So c times x. And then after that, we're going to substitute the value of x. So we now have c times the quantity or the ordered pairs x and 2x. By distributing C to each of the coordinates in the ordered pairs, we now have Cx and C2x that are elements in R squared. So axiom number 6 satisfied. Let's move on to the number 7 axiom. So C times the quantity of x plus y is equals to C times x plus C times y. So first, let's use this first part. Let's follow this first part. Let's copy C. Since C is a scalar, x is equal to x to x and y is equals to y to y. So again, let's substitute the value of x and y. So the value of x, of course, x to x, and y is y to y. So let's simplify first the terms inside the bracket. We're going to add the first coordinates in each ordered pair. So we have x plus y. And then the second one, 2x plus y. After that, we're going to distribute the scalar C to each of the ordered pairs. So we now have C times the quantity x plus y and C times the quantity 2x plus y. After that, again, we're going to distribute the scalar C to each of the term. So C times x times y. We have cx plus y, and then C multiplied to 2x and 2y. Then we have now C2x plus C2y. So from this form, we can also write it in this one. We have now cx, the cx, and 2x plus the cy and the c2y. So from that, we have observed that they have common the c. So we're gonna pull out the c, and then we have x2x, then same goes here. The common is the scalar c, so we're gonna pull out the c, and then y2y. As we can observe from our given, x2x is equals to y. I know, rather x. So this is x, and then y2y is simply means it's y. So from this, we can write it as c times x plus c times y. So indeed, from this, we can prove that c times the quantity of x plus y is equal to c times x plus c times y. Again, axiom number 7 satisfied. Next, we have axiom number 8. The quantity of c plus d times x is equals to c times x plus d times x, where the c, d there are scalars, and v, x rather, is equals to x to x. So we're gonna follow the first part of the axiom, which is this. So the quantity of c plus d times x, we're gonna copy the scalars c and d, and then substitute the value of x, which is the x and 2x. After that, we're going to distribute the c plus d to each of the terms. So we now have c plus d times x and c plus d times 2x. After that, we're going to distribute the x in each term inside the parentheses. So we now have cx plus dx, and then same goes here. the 2x will be distributed to each of the terms inside the parentheses. So we have c2x plus d2x. From this form, we can also write it in this way. So again, from this form, we can also write it in this one. There is still no changes. The value is still the same with this one and this one. So after that, since there is a common c and c, we're gonna pull out the c, and then x and 2x will be the remaining term, and then in this one also, d is the common, so we're gonna pull out the d, and then leave the x and 2x inside the parentheses. So again, as we can observe, x2x is simply means vector x. So from that, we can write it in short like this: c times x plus d times x. So again, from this quantity of c plus d times x is indeed equal to c times x plus d times x. Axiom number 8 satisfied. And for our axiom number 9, we have c times the quantity of d times x is equals to cd times x. Let c and d be scalars, and x is a vector which have a value x to x. Okay, so again, let's copy the first part of the axiom: c times the quantity of d times x, and then still copy the scalar c times, still copy the scalar d, and then substitute the value of x, which is x to x. After that, still copy the scalar c, and then we're gonna simplify first the terms inside the parentheses. So the d here will be distributed to each of the coordinates in the ordered pairs. So now we have dx and d2x. After that, we're going to distribute again the c to each of the coordinates in the ordered pairs. So we now have c times dx and c times d2x. So from this form, we can also write it in this way: quantity of, or cd times x and cd to x. Since both of them have common, which is the cd, we can pull out the cd and then put the x and 2x inside the parentheses. So as we can observe, x and 2x is equals to x. So we can just write cd times x, or cd, with the symbol of scalar multiplication x. So at this point, we can now prove that c times the quantity of d times x is equals to cd times x. Axiom number 9 satisfied. For our 10th axiom, we have 1 times x is equals to x, where 1 is a scalar and x is equals to x to x. So we just simply copy 1 times x and then substitute the value of x, which is the x and 2x, and then distribute 1 to each of the coordinates in the ordered pairs, and then we have 1 times x is x, 1 times 2x is 2x. X and 2x is equals to x. Therefore, we now prove that 1 times x is equals to x. Axiom number 10 satisfied. Since r squared satisfied all the 10 axioms of a vector space, therefore r squared is a vector space over f, or the field. And that would be all. Thank you.